Hello friends, welcome to this class on state space techniques. This is part of our unit number 6, in which we have already studied control system fundamentals. We have studied mathematical modeling, we have studied block diagram representation, and we have also studied some of the controller basics. And thereafter, we saw how to construct the Bode diagram or Bode plots for analyzing system performance. Now, this state space techniques is a somewhat advanced topic, you can say, in automatic control engineering or control systems engineering. It's a purely mathematical approach. Only difference in our conventional mathematical modeling approach and state space techniques is that we identify what are the input and output parameters, and then depending on the type of system, let us say I'm talking about a mechanical system in which a familiar example of spring mass dashboard system is concerned. My output is displacement x and my input is force F. In such a case, I have my conventional mathematical model as F is equal to m s square plus bs plus k sort of thing. And here, as I said, my input is force F and output is displacement x. Now, in state space techniques or state space approach, I give importance to the changes in state of the system. Whatever was the displacement, output displacement at a particular instant of time, what are the changes in the state of that mechanical system? I give importance to that. And that approach helps me in analyzing the performance of a given physical system. Comparatively advanced approach, and mathematically speaking, I can simplify a complicated differential equation, and number of equations also I can reduce, or differential equations can be easily converted into some set of algebraic equations. And particularly if I got a multi-degree of freedom system wherein I'm likely to get more number of equations for solution, there my state space techniques can help me out in conversion of those differential equations into algebraic equations. Secondly, this approach helps me in making use of linear algebra concepts like matrix algebra concepts for solution of these multiple equations by using matrix analysis. And I can always make use of softwares like MATLAB for converting a given differential equation into state space equation and then getting the same results. What I'm ultimately interested in is what is the transfer function of a given system, or what will be happening to the system if I give this particular type of input. So that purpose is also served in a simplified way, but the technique is difficult to understand to some extent. And I have got the software tool like MATLAB, wherein if I just include coefficients of my differential equations or the coefficients of my transfer function, I can always, or the software can provide me with these state space equations automatically. So those sorts of software usage or the software techniques are readily available for solution of complicated equations. And one such approach, we are going to just have an introduction of the state space approach. Just please be attentive. In the introduction part, use of Newton's law and free body diagram typically leads to second order differential equations. That is, equations that contain the second derivative, such as x double dot. X double dot corresponds to d2x by dt square or d square x. The differential equations can be expressed as a set of, please be attentive, the differential equations can be expressed as a set of simultaneous first order differential equations. A set of simultaneous first order differential equations. What is happening? The second order differential equation is getting converted into first order differential equations. These are represented in the state variable form as a vector equation. So x dot of t, bracket t, what does it mean? By now we should be very clear with this concept now. Now x dot is a function of time, is equal to capital A into xt plus b into ut. Okay, so u is my input function, y is my output function, and x is my state variable, remember. And second equation, y of t, y output is a function of time, is equal to cx of t plus du of t. So I can convert those second order differential equations into these two set of equations. Now these are two equations are called as state space equations, where for an nth order system, A is an n by n system matrix. Now what is this n by n? Rows and column. N rows and n column system matrix. A is a system matrix. B is an n by 1 input matrix. B is n by 1 input matrix. What does it mean? N by 1 number of rows are there, but column is only 1. So what we call this as? We call this input matrix as column matrix. C is a 1 by n row matrix. So clearly it is mentioned. 1 row and n columns, isn't it? So it is a row matrix, referred to as output matrix. So this is the output matrix, this is the input matrix, this is the system matrix, and D is a scalar called the direct transmission term. The A, B, C and D matrices together define the system. So my higher order differential equation, which is representing the physical system, in state space approach is getting converted to set of two equations. One is x dot of t is equal to ax plus, I'll not utter the word t now, it is understood now, it's function of t. So x dot is equal to ax plus bu and y is equal to cx plus du. So these two equations, if I am able to convert my differential equation into set of these two equations, I call that I have converted my mathematical higher order differential equation into set of state space equations. The column vector x is called as state of the system. The column vector x is called as the state of the system. The state, please be attentive, the state of the system is a set of variables such that the knowledge of these variables and the input functions will with the equations describing the dynamics, will provide the future state and the output of the system. So by solving these equations, what I'm doing? Future state means I'm predicting the performance of the system by solving these state space equations and predicting the system performance. In other words, the state variables describe the future response of the system given the present state. I have to give the present state and then predict the future state. Still working on paper. Remember, in control system engineering, we are working on paper. We are using the tools of mathematics for predicting the system performance, and state space is one such approach. The excitation given the present state, the excitation inputs, and the equations describing the dynamics of the system. For mechanical systems, the state vector elements usually consist of positions and velocities of separate bodies. As we have been saying, for mechanical systems, for translational mechanical systems, what we said, force is the input and displacement, velocities and accelerations are normally the outputs. So the ordinary, in block diagram format, the ordinary differential equations which are obtained from the laws of physics not only can be converted to state space form, but also to transfer functions. This handout explains the procedure to be followed to convert ordinary differential equations to state space form. The following diagram explains in detail the relationship between the various representations of physical systems. So what we do, ordinary differential equation, we take a Laplace transform, convert that time domain equation to Laplace domain equation or S domain equation and take the ratio of output by input, I get a transfer function of that system. And from that transfer function, if I take inverse Laplace transform, I can get the time domain equation or the time domain solution. Now, there are two cases. These ordinary differential equations can be converted into state space equations. So equations, ordinary differential equations converted directly into state space equations, and second approach is transfer functions can be converted into state space equations. What are the procedures? We'll briefly see. The first case is formulation of the state space equation from ordinary differential equation. So the first case is formulation of the state space equation from ODE, that is ordinary differential equation. In general, please be attentive. In general, an nth order differential equation is given as, in general, an nth order differential equation is given as dn by dt raised to n, the nth order differential of function yt plus, so descending order of the differentiating terms. Okay, so maybe d cube by dt cube y of yt plus a1 into d2 by dt square of yt plus dot dot dot, so an is equal to f. This is a generalized form of the ordinary differential equation that we come across. To reduce, please be attentive, to reduce the above differential equation into a system of first order differential equations, let yt is equal to x1. Please be attentive. Yt is x1. So dy by dt is x2. Okay, yt is x1, dy by dt is x2, and d2y by dt square is x3. So this is how I replace yt, d2y by dy by dt and d2y by dt into x1, x2 and x3 terms. Like that, I go up to nth term. From the first two equations we have, okay, from the first two equations what we have is x1 dot is equal to dy by dt is equal to x2. Sorry. x1 dot is equal to dy by dt, that I call it as x2, right, which is the first order differential equation. Note that in the above equation the dependence of t is implied, right, and hence dot from the equation. So t, bracket of t, he has eliminated, that's what he says, bracket of t is eliminated, now it is implied. Similarly, from the second and third equation we get the first order differential equation. x2 dot is equal to d by dt of dy by dt, that is d2y by dt square, that is equal to x3. x3, d2y by dt square is x3, dy by dt is x2, so yt is x1, right? So what does this mean? dy by dt, yt itself is x1, so it is d of x1 by dt, isn't it? D of x1 by dt is nothing but x1 dot, so y2 is equal to x1 dot, isn't it? And similarly, x3 will be equal to x2 dot, because x2 is dy by dt, d by dt of dy by dt is d2y by dt square. So x3 is x2 dot, x2 itself is x1 dot. That's what this says. x2 is x1 dot and x3 is x2 dot, right? By following the above procedure for the next two equations, we get another first order differential equation. In this manner, we get n minus 1 first order differential equations. Now substituting the above relations in equation 2, what we get is the differential equation is getting converted into simple algebraic equation, right? X of n plus a1 into xn plus dot 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 a n minus 1 of x2 plus a n x1 is equal to f, right? That implies xn is equal to, taking all these terms on the right hand side, xn is equal to f minus, all these terms are taken on the right hand side, minus a1 xn minus so and so an x1. So this is how the differential equation is getting converted, higher order differential equation is getting converted into first order set of differentials, set of algebraic equations, right? From the above equations, it can be concluded that the nth order differential equation has been reduced to n, please be attentive, the nth order differential equation. The third order differential equation will be converted into 3 first order differential equations, right? Or fourth order differential equation is converted into 4 first order differential equations. So simplification is all. Representing the first order differential equation in the form of a matrix, we have x1 dot to xn dot is equal to. So this is the multiplication matrix, that is matrix of constants, that is A into, that is called a system matrix, and this is my state matrix x1, x2 up to xn plus input function matrix, right? Ut is input function, f is the input, and x is the output, isn't it? Which is similar to the first equation of equation 1, which was x dot of t is equal to ax of t plus b of ut, or just eliminating t because we already know that all these are functions of time. X dot will be equal to ax plus bu. How it is obtained? Just by rearranging, by converting those differential equations to set of algebraic equations, and then just rearranging the equation f minus a1 xn up to an x1. Right? So this is one of the state space equation. Let us take a simple example. Consider the mass damper system shown below. The objective of this example is to write the governing differential equation in the state variable form. Now this is the familiar example. I have a mass, I have force as the excitation force, external force as the input, and I'll be getting y as the output. The y is not shown here. Y as the output displacement that I'll be getting. So what will be the equation? If you remember, F is equal to inertia force, that is y double dot, that is md square y, plus c is the damping coefficient, cdy plus ky, right? F is equal to my double dot plus cy single dot plus ky, right? So there we used the parameter as x. Now we are using the parameter y. Okay. Otherwise the equation is same. So it is nothing but md square y plus cdy plus ky is equal to f, or m s square in Laplace transform terms, m s square plus cs plus k is equal to f, right? So I can get the differential equation like this. It can be seen that the above differential equation is of second order. To reduce it to first order differential equation, let y is equal to x1. Let y is equal to x1. So dy by dt is equal to y, that is equal to x2, right? Sorry, dy by dt is y dot, that is equal to x2. So this is y dot is equal to x2. So in this case, the states of the systems are, states of the system are x1 and x2, two states, x1 and x2, which are equal to y and y dot, respectively. From the above relations, it can be concluded that x1 dot, this dy by dt is nothing but dx1 by dt. So it is nothing but x1 dot. So x1 dot is equal to dy by dt is equal to x2. x1 dot is equal to dy by dt is equal to x2, which is the first order differential equation, right? Which is the first order differential equation. Substituting the relations 4 and 4 in equation 3, we get the second first order differential equation. So this is the second first order differential equation. So this second order differential equation, which was m into d2y by dt square plus c into dy by dt plus ky is equal to f. This is the original second order differential equation. It is getting converted into m into x2 single dot. So first order, then it was second order, x2 single dot plus cx2, because x2 was equal to dy by dt, plus k x1 is equal to f, right? Solving it for x2 dot now, right? So I'll be taking remaining terms on the right hand side. So f minus cx2 minus kx1. So x2 will be equal to mx2 dot will be equal to f minus cx2 minus kx1, and dividing all the terms by m, what you get, x2 will be x2 dot will be equal to f divided by m minus c divided by m into x2 minus k divided by m into x1. So this is how I rearrange that equation. And then in matrix form, the last expression in the form of a matrix, we have x1 dot x2 dot is equal to, so how do we get these? So a row into this column, so 0 into x1 plus x2, so x2, and so this will be the x2 part, and then minus k by m into x1 minus k by c by m into x2, right? This c by m into x2 minus k by m into x1, right? And f by m, right? So f by m, here it should be 1 by m, right? Correction, 1 by m. So f by m. So this will be my matrix converted equations. If, for example, we are interested in measuring the velocity of the mass, then the output of the system is the velocity of the mass. In other words, y is equal to x2 is equal to row matrix 0 1 into x1 by x1 x2, column matrix x1 x2. Equation 7 and 8, which are similar to equations 1, represent the state variable form of the above defined system. Please refer to it frequently, read the books. I'll provide you 4 more notes also, so that the concept will be more clearer. You can refer a book by Ogata, which describes the state space analysis very nicely. The Modern Control Engineering by Ogata, so the concept will be more clearer. Even in Ravan's book, you'll find concepts of state space techniques. Even in Bolton's book, to some extent, he has described briefly the state space approach. So F is the input of the system, x1 and x2, which denote the position and velocity of the mass, represent the states of the system, and y is the output of the system. So comparing these is 1 and 2, I get A, the system matrix, as 0 1 minus k by m minus c by m. B is the output matrix 0 1, and C is the system matrix, right? C, I don't remember. C is so what was C? C was A is the system matrix, B is the input matrix, C is the output matrix, and D is the direct transmission term. D is the output matrix. So here C is the output matrix, C is the output matrix, input matrix, system matrix. Now second case was, so the first case was related to how to convert the higher order differential equation into a set of single order differential equations by using state space approach. Second case is, given the transfer function, formation of state space equation from transfer function. There are various ways in which A, B, C, D matrices can be represented. These various ways of representations are called as canonical form of state space. One such form is control canonical form. Consider the transfer function f of s, which is equal to output by input Ps by Qs is equal to b1 into s to the power n minus 1 plus decreasing powers plus b2 into s to the power n minus 2 plus dot 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 plus bn. So like I have got a transfer function as s cube 2s cube plus 1s square plus 3s plus 50. Right, so we have to identify what are b1 b2 coefficients, right? We have to arrange the numerator in the order of decreasing order, right? In the denominator also I have s to the power n plus a1 into s to the power n minus 1 plus dot 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 an, right? So s square plus 4s plus 15, like that I have got a transfer function. I have to just amplify, identify what are the coefficients of those transfer function numerator and denominator. I want to convert, my objective is to convert this transfer function into state space equations. Then the control canonical form is the system matrix is obtained from A1, A2, An, right? Minus of A1, A2, whatever is the coefficient. I have to just note down from the transfer function and substitute it in this matrices. In this matrix, I get system matrix. B is a column matrix, 1, 0, 0, 0, and C is input matrix. Output matrix. B was the input matrix. C is the output matrix. So this is the output, right? So B1, B2 I have to identify and I have to just put it in row matrix. D is equal to 0. So just let us take an example. Write down the state space matrices based on given transfer function. So Ys is equal to numerator is 2s square plus 3s plus 1 and input denominator is s cube plus 4s square plus 6s plus 5. Comparing the given transfer function to equation number 16. Right. Identify what are B1, B2, B3, A1, A2, A3. B1, B2, B3, A1, A2, A3. 2, 3, 1, 4, 6, 5. Based on the values of A's and B's, the system matrices can be written as, we already have that format. A1 to N as the row and row matrix is B1 to Bn. B1 to Bn. Right. So B1 to Bn, 2, 3, 1 is here. Row matrix 4, 6, 5, minus 4, minus 6, minus 5, 1, 0, 0, 0, 1, 0. B is equal to 1, 0, 0. So I've identified from the transfer function, I've identified the system matrix, the output matrix, and the input matrix, right? So MATLAB, as I told you, MATLAB toolbox can be used. Let the transfer function of a system be called as, be defined as f is equal to 1 upon s square plus 2s plus 1. Find the state space form of the above transfer function. So I use the command maybe TF to SS, TF number 2 to SS, right? So TF to SS is the command that is used. So I give the numerator values, I give the denominator values because in the numerator I got only 1. Numerator value is 1, denominator is 1, 2, 1, 2, 0, denominator is 1, 2, 0, coefficients of the denominator 1, 2, 0. So ABCD is the TF, as I told you, the command in MATLAB is TF to SS, transfer function to SS, that is state space, transfer function TF to state space, in parentheses and bracket numerator and denominator. And the MATLAB, at the click of the button, will give me the matrix A, matrix B, matrix C, and matrix D. So this is how the MATLAB code can be used, or MATLAB toolbox can be used for converting, for getting the state space representation equations or state space matrices from the transfer function. So this is how briefly I have discussed this concept. It's a bit difficult concept to understand, but I think it's an introductory part. You refer the books. You have got number of videos available on YouTube. In Indian author books also, a lot of material is available. As I told you, even in F.H. Raven's book on automatic control engineering, the state space techniques are discussed in depth. Because it is just an introductory part in our curriculum, I have discussed it briefly. So thank you for watching, friends.